All right, thank you. Okay, so here's what I want to do today. I want to go back. I'm going to spend a little time going back over the big aha of the control part, just to make sure we all got it, because it kind of happened at the end of last lecture, and then I'm going to start into our next topic, which is probably I think our last version of parallelism, which is instruction level parallelism based on pipelining. Before I do that, though, I just want to let you know that everything you're studying now will someday be obsolete. That's the bad news. The good news is it's probably still a long way away, so you don't have to worry about it too much. But, this is an interesting article that just popped up in this weekly newsletter that I get. Basically, it's kind of interesting, right? Computer circuits are super fast. They process, billions of clock cycles, billions of instructions a second. And the brain, right, neurons in your brain are a lot slower than that. They fire maybe at most 100 times a second, and that's on a good day. And so you might wonder, why is it that the brain can still do things that computers can't? And it has to do, not surprisingly, well, we don't really know, but we think it has to do with parallelism and interconnectivity. And so there's a bunch of people that are basically saying, all this stuff that we're learning in 61C, where you have an instruction pipeline and you sort of just try to make that go faster. And if it's not fast enough, you try to make more pipelines. That's really not what you need to do. What you really need to do is try to replicate the way the brain does computation. And this is just one story that happened to pop up about a group in Japan that's been working on that, and they've been they've come up with this new the use of this fancy sounding molecule to do computation. So not anything you have to worry about right now, nothing that's going to be on our final, but if you were to take this class 50 years from now, maybe it'd look more like that than what we're going to talk about today. But you don't have to worry about it right now. Okay, so the goal today, close the loop again on the control, and then start on instruction level parallelism. So here's where we ended up last time. That's our data path. It's got all these control signals that if you set them the right way, they'll do the instruction you want. Okay, we have also an instruction fetch pipeline that also has a control signal, plus it takes an output from the ALU, and then based on that, either goes to the next instruction, which is the PC plus 4, or it goes to some location that you've computed relative to the current instruction because it's a branch was satisfied. And we didn't talk about this in class, but it's in the book, maybe it's a jump. Maybe it's a jump routine, and you're going to go to some exact location, some other instruction. Okay? And the control signals we have are these up here. Okay? And so they're just put there, not because you're supposed to read through them all right now, but just so you have them in a list. Okay, so where do these control signals come from? Is it magic, right? And as we discussed last time, it's not magic. And in fact, not only is it not magic, but you already know how to do it, and you've known how to do it even before the previous lecture. Okay, so it's not that you know how to do it because you've seen these slides once already, but you knew how to do it already from the stuff that we've talked about. And so the basic idea is we're going to pull a 32-bit instruction out of memory, and some of those bits are an opcode, some of those bits are a function code, and those bits are going to be electrical signals, right? They're going to be high voltage or no voltage, right? 0 or 1, and then based on that, that's going to drive the circuit that's going to set all those control flags to be the right thing. So what we need to do now, just to close the loop, is to design that circuit. Okay, and how we're going to design that circuit, we're going to do it the way we always do. We're going to come up with a truth table. We're going to convert that into some Boolean expressions, and then we can assemble the gates to actually compute those Boolean expressions. All right? So all you need is these bits coming in off of each instruction. We're going to put them through that logic, and out is going to pop all these control signals set the way we need them to for that particular instruction, and then that's going to make all this stuff do the right thing. Okay, so any questions about it at that level so far? All right, because this is really where it comes together. Okay, I'm not going to spend any more time on this, but this is just for your edification and your studying later. This is the register transfer language description of all our instructions. Remember, we're not doing all of MIPS, we're just doing this MIPS Lite subset. Okay, so if you look at that, that tells you what you need to do. You can compile that into a truth table, and I guess the interesting things to see here are, here's the opcode. Right, so we got 6 bits of opcode. In the case where the opcode is not 0 in our set, we don't care about the function code. If the opcode is 0, that means it's an ALU instruction. We don't know which one, so we look at the bits of the function code, and that's going to tell us that. Right, that's going to tell us which ALU function we're going to implement. And then if you map that out, it maps all to these 1s and 0s. And there's a couple things here you should just notice. So 0, you know what that means. 1, you know what that means. X, that means we don't care. And you notice the ALU has some funny things here, these add, subtract, or. Those are the 3 things that our limited ALU does. It's going to turn out, because we have to represent 3 different values for the ALU control, we can't do it with 1 bit. We need 2 bits. So we'll have to set those 2 bits. So that's all that. So add means the 2 bits set to do an add, the 2 bits set to do a subtract, 2 bits to do an or. Okay? But it probably should have just done it. We'll do it on the next slide. But anyway, it's basically just a truth table with a couple values where we don't care what they are because they're not relevant to our instruction. Yes, sir. Okay. That's a really good question. I mean, so that's good. So the question is, what is this notation here? And it's supposed to be that it's 2 bits. I'm not sure what that notation is trying to say, actually. So don't get hung up on that notation. Okay? Because we've got 2 bits. Our ALU controller is 2 bits. I'll show you how they're set in a second. Okay. Any other questions about this? Again, it's a bit of an eye chart, but again, you should just look at it and make sure it makes sense when you're studying this stuff. Okay, so given this truth table, now we've got to go and implement our circuitry. This is it. This is where it all comes together. So we've got stuff coming in from the opcode. We've got 6 bits of opcode, and those are actually the high order 6 bits of the instruction that we grab out of memory. We've got 5 bits of function code. Those are actually the low order bits. Oh, that should be 0 to 5. Okay, do we have 6 bits of function code? I guess we do. All right. That's it. We're not going to use them all, but that's the low order bits of the instruction. Okay, so we're going to look at the opcode for sure, and then if the opcode is 0 in our limited instruction set, opcode 0 says you also have to look at the function bits. And again, all that stuff is in the instruction. Okay. Now, what if the instruction is an opcode that's non-zero? Well, these function bits will be something else. They'll be, whatever those bits were set for that instruction. So if it was, say, an immediate instruction, like a load word or something like that, it would just be whatever bits there were in the offset or whatever. But it doesn't matter because we just won't look at them. Okay. So the only time we're going to look at the function bits is when the opcode is 0, and then they better be set the way we need them to be. All right? So great. So good. So now given that, how do we decide what instruction we're running? Well, we know what our opcodes are, and so you can basically just write the expressions that tell you what the opcode, what for a given set of bits in the opcode, what instruction that is. Okay, so for example, we know an R-type instruction, everything's going to be set to 0. So it's opcode, so bit 0 of the opcode is 0, bit 1 is 0, bit 2 is 0, and bit 3 is 0, 4 is 0, and 5 is 0. If all that's true, then R-type instruction, that variable R-type is set to 1. If any of those bits is set, that means it's not an R-type instruction. That means it'll be set to 0. Okay? So it's just an AND of all those things. Likewise, if you look at the opcode for ORI, basically it's 1 0. I'll read this way: 0 0 1 1 0 1. Okay, and so you just do the ands. You just do you AND you know, whether you need a 0 or a 1 there. Okay? And so these are just the expression for, we have this definition of for each opcode what its binary representation is, and this is just the expression for that binary representation. Okay? So now, given an instruction, we look at those high order 6 bits, and we come out with one of these has better be set to 1. Okay? Otherwise, we don't know what it's an instruction that we don't know, and that's going to be an error. Okay? So exactly one of these should be set to 1. All right? Now, we're in good shape, so if the opcode is an ORI, we're done because ORI will be set to 1 and all these others will be set to 0. If it's a load word, then LW will be set to 1 and everything else will be set to 0. That's great. The only time that we're not completely done yet is that case when R type is set to 1, which means everything else is set to 0. Okay? And then, if that's what's going on, well, we've got a little more work to do because we know we're going to be doing an ALU instruction, but we don't know which one. So now we've got to figure out which one. So we've got 2 that we're going to choose from here, 2 arithmetic instructions, an add and a sub, and to tell which one that is, we've got to look at the bits in the function code. And so that's what we're doing here. Okay? All right, so good. So that's how we figure out what instruction we're running. We look at the opcodes, and if necessary, the function codes. And how do we implement this in gates, right? If you're going to build the circuit that produces a 1 in exactly the right case, what are you going to use for gates to do that? Too simple, right? Because everything here is an AND. There's no operation here. Well, you've got some inverters, I guess, but you're going to build this thing out of AND. You're going to actually use AND gates to compute all these. You're going to put inverters in wherever you need the thing to be 0. All right, so it's just AND logic. So, yeah, go ahead.
I have a question. So you're deriving those numbers based on what the opcodes for add and sub are. Are those opcodes arbitrary, or are they designed in a way such that the particular wires that are on and off are more efficient?
Okay, great. So we're using wires to drive all this. Is it arbitrary, or is it set in some way to be more efficient? I don't actually know the exact answer to that. You can imagine that there's an argument for why you might want the R-type thing to be 0, 0. But I think in general it might matter, but you could do it either way. There might be a way to make it more efficient and pick these bits carefully. But as you're going to see, it's all going to go into a circuit, and then these control signals are going to come out. So it might not matter that much. All right, but I hesitate to say no, we don't worry about it, because chip designers worry about everything, right? And any place you can get a little advantage, you try to do it. All right, any other questions? Okay, well, what's this going to look like? This is awesome, right? So opcode comes in, function comes in, right? There's 6 bits there. There should be a 6 there. There should be a 6 there, right? So we've got 12 bits coming in, and what comes out of this box is what do we got here? 3, 7, and we didn't really look at jump, okay? And how many of those lines are going to have a 1 on them? Exactly 1, okay? So you'll have 1, and then everything else will be zeros. Okay, great. So now we know what instruction we're running. So remember, that's what we're going to do. We're going to figure out what instruction we're running, and then we're going to set the control signals to make our circuit, to make our data path implement that instruction. Okay, so any questions about how we go from 32-bit instruction to getting these lines with the right values on them? All right, you just fill in this box with a bunch of AND gates and some inverters. Okay, great. So now we've got to just fill in the second box. All right, what's that going to look like? Well, that's going to look like this. Here are all our signals. And by the way, I think when I printed those slides out this morning, there was a little bug on that slide. So just make sure your ALU controller value 1 just says OR. I grabbed it from someplace. I had a cut and paste mistake, and I don't think I caught it till after those things got printed. So, and it was correct when I showed you this slide last time. So somehow I messed that up. But anyway, these are all our signals, right? Because remember, let me just go back. Here's what we're trying to do. Instruction comes in, comes through this magic box that we're creating now, and out come all the right signals. So we've got to finish that. So that's where we are here. And basically, this is how we set those signals. So we've got all these lines coming in, right? Add, sub, ORI, LW, SW, branch on equal, jump. Okay? One of those will be set. The others will be, or asserted. The others will be deasserted, or 0. Okay? And then you just run it through this logic. So if the add line is asserted or the sub line is asserted, then I assert reg destination, right? That's going to be 1. Remember, that's going to tell us, you know, that flag is the one that what? Tells us which register we're going to write, if it's register D or register T. Okay? The ALU source, we're going to have that one set if our instruction is ORI, or if it's LW, or if it's SW. Okay? Mem to reg, right? That's the one that tells us when we write a register, does the value that we're writing come from memory? If so, we set it to 1. Otherwise, it's going to come from the ALU. We set it to 0. Well, that one is just if our LW line is on, that's the one where we're loading something from memory into the register. So that'll get set to 1. Otherwise, it'll get set to 0. And you can just read down all of these, and you'll see that it's going to do the right thing according to you know, what we need our. Can somebody? Well, as long as he doesn't snore too loud. This is one of the worst moments of being a professor, let me tell you. Never happened to me, honest. Okay. All right, if he starts talking, then wake him up. Or listen to what he says. All right, here's the only other tricky one. This is the thing that's going into the ALU that's telling you what operation the ALU is doing. Again, we need 2 bits. And basically, if it's 0, 0, we want to do an add. If it's 0, 1, we want to do a sub. And if it's 1, 0, we do an OR. So the way you set that is the low order bit gets set to 1 if it's sub, or if we're doing a branch, that's fine. The high order bit gets set to 1 if it's an OR. Okay? Because remember, if we're doing a branch, what do we need the ALU to be doing? Well, the ALU is computing our address. Okay? So that's got to be an add. Oh, wait a minute. Did I screw that up? I'm sorry. I totally screwed that up. If it's a BEQ, I'm sorry. I did that way wrong. Let me do it again. BEQ, remember, we've got to test if those 2 values in the register are the same, if they're equal. How do we do that? We do that with a subtraction. Sorry. So if it's BEQ, we've got to set that low order bit to 1, because that's what tells it it's a subtraction. Okay? So forget what I just said. Okay? So bit 0 is set if it's a real subtraction, or if it's a branch on equal, because we're going to play that trick of using subtraction to do equality. If we're doing an OR, then we set the high order bit. Okay, otherwise it's going to be 0, 0. Okay, so how do we, okay, so is everyone clear on that? Hopefully I didn't confuse anyone with that. Okay, so now you see, oh, go ahead. Yeah.
Is this simple process of ORI or
Well, the ALU doesn't know that it's an ORI, right? The ALU, if you remember the circuit, we compute that immediate value before the ALU ever sees it. So we get the right. So we sign extend it, and it just thinks it's doing an OR. Yeah. So all that stuff has to happen before you get to the ALU, and the ALU just thinks it's doing an OR. Yeah. Yeah, that is what I just, oh, okay. Oh, I see. Oh, yeah. You know what? I think I screwed that up when I was fixing the slide for some definition of fixing. Thank you. Okay. That was my bad. Right, because we don't have a signal called OR in this. So there it is. Sorry. All right, so make sure you get that right. Thanks for pointing that out. And thanks for pointing it out when I missed that that's what he was pointing out. All right, anything else about this? Okay, so what's that going to look like? What are the gates for that? You already know how this game is played. There's nothing up there but ORs. So That's going to be OR logic. So this is our whole controller. Okay, opcode and function come in based on that AND logic that we had on 2 slides ago. These signals are asserted or deasserted. Based on whether those are 0 or 1, we run it through that OR logic we just created, and out pops all the right signals. Okay, that's how it all works. That's how those signals get set. And that's why I wanted to spend some extra time on it, because that's the fundamental thing. Okay? So, so here's where we are, right? We finally kind of put the pieces together. This is what Dan was promising us when he started talking about the way this course is built. We started here at C. We translate things into MIPS. We translate our assembly language into machine language, right, which is just ones and zeros. Right? And we just talked about how those ones and zeros drive all the logic, okay? And from the bottom up, we did the transistors. We talked about how to turn that into these blocks that do something. We put those together into a data path with control signals coming in. And then what we just did is that. We just put it all together. And when Dan shows this slide, there's music and stuff, and I'm sorry. There actually is music, so there we are. That's it. So we made it, and the rest of the semester we're just going to coast. We're done. Well, not really, but that's what we've done. Okay, so with that as the grand finale for that part of the class or that discussion, are there any other questions about this before we move on to from this nice simple world we constructed and make it a little more complicated? And realistic. But not so far as to go with the organic molecules. We're not going that far. Yeah?
Can you deal with the CPU? Do you have like a separate piece of logic and a separate ALU, or try and integrate everything?
Oh, okay, great question. Oh yeah, so what was the question? The question is, when we deal with the PC. When we deal with the PC, do we have a separate ALU, or do we have separate logic in its own ALU, or do we try to use the main ALU? And the reason that's a great question is because that was one of my peer evaluation, peer education questions, like the clicker questions. But I just couldn't get my clicker stuff together again. But so that's one of the questions. So I guess I'll just ask people, do you think is it a good idea to try to save some gates? The way we've been drawing the PC logic is it's had its own adders, right? We weren't using the main ALU. Does it make sense to try to use the main ALU? Is there a good argument for doing that, or a good argument for not doing it? You could save yourself some gates if you do it. What's the problem with doing it?
Doesn't that decrease the efficiency? You have to go through
Well, right. So the problem is if you do that, you're going to have to go through the ALU, that one ALU you have, 2 times in a single instruction, and that's going to lengthen your clock. So you could make it work, but then you'd have to get the timing right so that you could make it through the ALU twice and still have your signals all be set it the right way. Okay, so we're going to be able to make the clock tick much faster if we have separate ALU to do the address manipulation or the PC manipulation. And we'll keep the main ALU for doing the stuff we need it to do. Yeah?
But aren't we just implementing a single cycle CPU right now?
We are. We're implementing a single cycle CPU, but remember that whole path, all that stuff has to happen within a single clock tick, right? And that includes making sure the control bits are set at the right time and all this. And so it would be tricky to get the control bits set one way to do the PC calculation, get them set a different way to do whatever manipulation you have to do, all within the same clock cycle. And the other thing to keep in mind is that the ALU that we're going to build to manipulate the PC can be simpler because it's only doing, we have one that's only adding 4, like every time, and we have another one that's just always doing adds, and so those can be simpler. Okay, so the answer that I had to, is it a good idea to try to reuse the ALU to also do the PC manipulation was that no, it's not a good idea because it's going to make our timing way too complex. Okay? All right. So good. So let's take a quick administrivia break. This is important. So here's the story. So if you look at the schedule, Project 4 is due it's due the Sunday right before the last week of classes. And the way we grade Project 4 is we do it in person in lab. Okay, and labs start on Wednesday. So if you do the math, you realize you can't, it means you have to have your project done before Wednesday in order for us to do in-person grading. So what we're doing here is we're saying, okay, for Project 4, we're only going to allow at most 2 slip days. Okay, so you had 3 in the bank. You still have 3, but only 2 of them are usable for Project 4. Okay, so what does that mean? Well, what that means is, does that mean you should goof off an extra day this week? Probably not, right? But it's just giving you a heads up that if you're going to use your 3 slip days, use one before you get to Project 4. Okay, and it's just an unfortunate way that the classes, the semester worked out this way, that we had to do all our labs on Wednesday. Okay, so that's just it. Just you only get 2 slip days on Project 4. This will be posted on Piazza if it hasn't been already, but just so you have a heads up. Okay. All right, good. So let's move on. So we're going to keep in the same general subject, but now we're going to break down that assumption we were making about a single cycle CPU, right? So before, remember, we had one long clock tick, and we're going through our 5 stages of instruction execution, all within that one long clock tick. Okay. And what we want to do instead, well, okay, so let's just talk about that for a second. So let's say, here's how long things take. It takes 100 picoseconds to read a register or to write a register, and 200 to do anything else. Okay? So if you look at our instructions, like load word, store word, whatever, here's what they do. Load is kind of the worst, right? Because load does everything. It does every stage. So instruction fetch costs 200, register read costs 100, ALU costs 200, got to go to memory, that costs 200, and got to write a register, that costs 100. So that's 800 picoseconds. Okay? The other instructions are a little faster than that because they don't do all the stages. Okay? They don't need all that time. So the first question is, if this is my instruction set and this is how long things take, I'm doing a single cycle CPU, what's the fastest my clock can tick at, possibly? 800, right? This is it. This is the fastest I can make that clock tick, because I've got to be able to handle any instruction within a clock tick. Okay? So if you think about it, I'm doing a lot of other stuff. I'm doing stores. I'm doing a lot of R instructions, right? I'm doing a lot of arithmetic, right? Do some branches and so on. Doesn't matter. Even though those guys are faster, I'm limited by that critical path, that longest path through the whole circuit. Okay? And because of that, single cycle CPU, that's a hard thing to say, is going to be, that's the fastest it can go. All right? So, so what can we do? What do you got to do what can we do to improve the clock rate? How do we make that thing tick faster? I don't know. Does anyone have any ideas how to improve the clock rate? Yeah? Yeah. Anyone who doesn't already know the answer have ideas on... Okay, the answer was put registers in. What else could you do? Oh boy. So could you vary the clock rate depending on what instruction you're running? It would be really... No, I don't think so. It'd be interesting to try, and I'm sure somebody has, but it'd be really complicated to get that to work. Yeah, in the back. Yeah, so we're going to try to, okay, I think what you said is to kind of overlap instructions, and we're going to end up doing that. Yep. Yeah, you could, right. You could, you could try to make your circuits run faster somehow, right? You could try to put things closer together maybe so that you don't need so much time to go through. There's a bunch of things, you could do. But in general, it's going to, you could try to implement it on a faster, you try to make the chip smaller. That's going to make things run faster. You try to implement it on some other type of material that might switch faster than this. There's a bunch of tricks you can play, and some of them are going to let you make that clock go faster. Okay? Yeah.
If you know that every instruction is going to take, say, at least 300 picoseconds till the ALU, then you can actually have your clock tick before the register, right? Or, no, wait, actually, the register
Yeah, the register doesn't get written until the clock ticks. Okay, so I think the bottom line is, yes, there are things you can do, and yes, people try to do them, but we're going to do the thing that you guys first said, which is we're going to pipeline things, right? We're going to figure out, we're going to go away from this. Right now, we're stuck because we have this critical path, and the clock tick is determined by that critical path. And if you think about it, we're being kind of wasteful, because that critical path is driven by, well, first I've got to fetch an instruction, then I've got to decode the instruction, then I've got to do my ALU, and then, and while we're doing each of those steps, the hardware that we've designed and we've built to do the other stuff isn't really doing anything. It's just waiting for that clock to tick so that it can do its next thing. Okay? So, what we kind of want to do is parallelism, right? That's one of the big themes of the class. We want to get as much stuff as we can running in parallel, okay? Because that's going to shrink the time. So here's the pipelining analogy, all right? So you got to do your laundry, and let's say you've got 4 people who need to do laundry, and let's say that there are 4 steps for doing laundry, and each one takes 30 minutes. So you'll notice this is a somewhat contrived example, okay? But hopefully it's instructive. So you got to wash the stuff, takes 30 minutes. You got to load it in the dryer, you got to fold it, you got to put it away. And each of those steps takes 30 minutes. Okay, so when you do this, and if you study computer science long enough, unfortunately, this is the way you start looking at the world. It's really not pleasant. But you look at it and you say, okay, well here's what we've been doing this whole time, right? I forget, is that Alice or whoever A was, is going to do her laundry. That's going to take 2 hours. And then Brian's going to come along and do his laundry, and that takes 2 hours, and so on. So how long does it take to get 4 loads of laundry done in a single cycle laundry machine, which is what this is? And the answer is it takes 8 hours. So it takes you 8 hours to do 4 loads of laundry. Okay. Well, this is the thing we want to do better than. So what can you do? Well, you can do laundry pipelining, and this is actually what you would do. You'd say, okay, I've got 4 people who want to do their laundry, so I'm going to do it this way. Alice is going to use the washer. As soon as she's done, she's going to put her stuff in the dryer at the same time. The washer's now sitting there doing nothing. So Brian can come along and use the washer. Right? 30 minutes later, Alice is done with the dryer, so Brian can use the dryer. She's done folding. Oh, no, she can fold, and Charlie can go ahead and start using the washer. So we're going to keep all our resources busy the whole time, okay? So we had, 4 people doing laundry. Each item of laundry takes, it takes 2 hours to do your laundry, okay? So before, 4 people, it took 8 hours to do their laundry. Now how long does it take for 4 people to do their laundry? It takes 3.5 hours, okay? So that's pretty good. So we've more than halved the time it takes to do the laundry. Okay? Now here's the tricky part. All right, the tricky part is, have we actually made doing laundry from the perspective of Alice any faster, right? Alice showed up at 6 o'clock. She started doing her laundry. When she was done, it was 8 o'clock. So life hasn't changed for Alice. Okay? So in general, we haven't solved the latency, right? From the time you start the job to the time it's done, we haven't sped that up at all. That's kind of interesting. But what we've done is we've increased the throughput. Okay, so latency stays the same. Throughput has now gotten much better. Okay, we used to be able to do, 4 loads in 8 hours. Now we can do 4 loads in 3.5 hours. Okay? So our throughput's gone way up. And the trick that we used is exactly this one that you guys were saying, which is, hey, why should we have all these idle resources just sitting there? Why don't we try to use those? Why don't we try to get all that stuff happening at the same time? All right? And so what's interesting here, though, is 2 things. So first of all, we kind of didn't get the maximum speed up we might have gotten, right? Because you'd think, okay, I've got 4 resources, I've got 4 people doing their laundry. I should be able to speed things up, I should be able to get things to go, take 1/4 of how long they were taking before. And I didn't quite get that. And the reason I didn't get that is because it takes a while for the pipeline to fill, okay? You'll notice there's only one time here when all the resources are being used. Okay, so there's this startup phase where the pipeline has to fill, okay? And then there's this kind of ending phase where as jobs finish, if there aren't any new jobs coming in, then you're also underutilizing your resources. A bunch of resources are going unused. Okay? So it's not quite perfect, but the more work you have, the more jobs you have, the less these edge effects are going to matter, right? And the more that you'll be running all the time with all your resources just running. Okay? So that's kind of the idea. The other thing, by the way, to notice is life does get better it doesn't get any better for Alice, but it gets better for everybody else. Okay? Because they don't have to wait as long to get started. Okay? So it does kind of help, the amount of, the delay that when a job comes to the system, that job is going to start sooner. And so it does reduce latency that way. But if you actually look at completion from the time the job starts to the time the job finished, that doesn't change in this scheme. Okay, it's just the waiting time is going to change by a lot, hopefully. Yeah. Okay, that's great. We're going to talk about that next. So right now, all the steps are taking the same amount of time. Is that what we want, or could we do better maybe if some of them were faster than others, or would that be worse? Yeah. Yeah. Okay, so great. So this is another great question, which is, what if Brian forgot his laundry detergent, right? So he goes over to the washing machine. He's about to put the stuff in the washing machine. He says, oh, no detergent. So what's he got to do? He's got to go to the store and get some, or maybe there's a machine there, but he forgot to bring change. Maybe he asked somebody else. But yeah, that's going to mess things up too. Okay? So the question wasn't about washing machines, it was about memory, right? And what if I have a miss in my L1 cache? Well, guess what? All of a sudden that starts messing up the pipeline too. So that's called a pipeline stall. And you have to decide what you're going to do. Are you going to make everybody wait, or are you going to let somebody jump ahead? Okay? And we'll talk about that stuff, in another lecture or two. There's a question here.
So is there also a way
I'll get to you in a second. Yeah, go ahead.
it really wouldn't work too well with our type though, right? Because if you have to write a register and then maybe the next instruction needs that moving value to the register, then you can't really pipeline it like this, right?
Okay, so the question was if I have our instruction where I have to write a register and the next instruction needs the value of that register, I can't pipeline it. I think you can, as long as you have time. We'll see what the timing looks like. And there's a little trick to make it work, but you'll see that it can work. Yeah, go ahead. Yeah, no, that's you, sorry. In the front. Front of the back. Yeah.
If you're using registers to store the data
Yep. Yeah, good. So let's look at how we're going to really, you guys already figured out how we're going to implement this. Okay? So let's talk about that. So, just a couple more lessons. There was a question about what if something goes faster. Okay, so let's say we buy a new washer, and now it only takes 20 minutes instead of, and a stasher, whatever that is. And let's say they take 20 minutes. The other things still take 30 minutes. Can we speed up our pipeline at all? You can't. The answer is no. Because at any step, somebody's going to be using the dryer and the folder, and those still take 30 minutes. All right? So again, this is one of these cases where you're limited, in some sense, by your slowest resource. Okay? Now, what's good here is we're not adding up the slowest resources. We're just taking, right, in the single case, the single cycle case, you take all those resources and you string them together, okay? And that's your delay. Now we're going to separate them. So we're not adding them together, but we're still taking the slowest one and saying that's how fast our clock can tick. Okay, but this is still a lot better. Okay? Yeah?
If the very last operation was faster than that, each individual job would be...
Yeah, okay, good point. If, in fact, since this stasher only takes 20 minutes, in theory, the end of this job it could end 10 minutes faster. Okay? So that's right. The problem is, if your clock, if this guy is doing something that the next guy is going to have to look at, like writing a register, then you got to wait. You know, it's not going to start until the next clock tick. So you're probably not going to get really much benefit out of that. Okay, but certainly for the laundry case, you would. All right. So you're limited by your slowest stage. And the other, and so you're limited by your slowest stage, and unbalanced lengths, it's going to reduce our potential speed up because, again, you're limited by this longest one, and we'll see that in a second. Okay, so let's look at how we're going to really implement this. Those are our 5 steps. They're what we've seen before: instruction fetch, decode, execute with the ALU, access memory if you need to, and then write back the data to a register. Okay, and they've just been given abbreviations here, but it's the same 5 steps we were doing in the single case, and that's what our single cycle data path looked like. Okay, so here's how we're going to do it, and a lot of you guys have already figured this out, and we've actually seen an example of this earlier in the class. What we're going to do, the way we're going to decouple these things so that they can all run independently, is we're going to put registers between them. Okay, so now. This stage produces a result into that register. This stage reads that register, writes a result to this register, and so on. So now we can have these things all going at the same time, and they just have to read, when they need something from their predecessor, they're going to get it out of that register. Okay? Yeah? How do you know that's the best place to put your register? Right.
But I think it's possible that 2 of the blocks could add up to be like only one of the other blocks.
Yeah, it's a good point that what we're trying to do, remember what we're aiming for is balanced stages. So you're right that in this case, we just took those 5 steps and we said, let's put a register between each of them. If there were 2 operations that could complete within the time that were next to each other, and that could complete within the time that one of the other steps already takes, then yeah, you could get rid of that register if you wanted to. Okay? So that is an optimization. Okay, but it's not going to make things run any faster. It's just going to save you a register.
But you could also take like your slowest block and try to chop that into.
Oh, absolutely. You could take your slowest block and try to split that into multiple pieces with a register. Sometimes that's going to work, sometimes it won't work. Right? Depends on what that block is doing. Right? It's hard to split an ALU, for example. Yeah?
How do you know that the values are still the most up to date?
How do you know that the value for the register will be most up to date? Well, let's look at an example, and then maybe it'll become clearer. So let me do this example, and we'll should have time for another question. So this is the same pipeline. It's from the book, it's got a couple extra lines in it, but it's basically the same thing. We've got our instruction memory, we've got our register file, ALU, data memory, and then we write the registers if we have to, right? So those are our 5 stages. And basically, let's do instruction fetch for load or store is going to look like that, right? We're going to fetch the instruction from the memory. We'll put it into the register. In the decode step, we read from that register, and then we get the stuff that tells us. Of course, it sets our control signals, and then it also gets the stuff out of the register file that we need. that gets written into this next register. Okay, in the third step, that's execution. So we read the stuff from that register, we run it through the ALU, and then we write to the output register. Okay, then we're doing a load here. Hold on just a second. So what we did in the ALU there, because we're doing a load, is we calculated the address that we're loading from. Okay, now in the fourth stage, that's when we access memory. So the address is in memory, in this register, and we read that from the register, and we use that to say, okay, look in here, look in the memory, and get the item out. Okay, again, assuming that it was in the level 1 cache. Okay, so we're almost done. That was 4 stages. We're about to do the 5th. Does anyone see a problem here? Yeah. Oh, jumps and branches. Absolutely. Jumps and branches is going to mess this up, and that's what we're going to talk about next time. But even for this load instruction, is everything okay? And I'll give you a hint. Look at the title of this slide. So is everything okay? Okay, so what are we going to do in the next step? We're going to take what came out of the memory and was sitting in this register, and we're going to write it into our register file. Okay? Now, how do we know? Oh, go ahead. Do you know what the problem is? Oh, we don't care if the register. Okay, we don't care if the this register. Yes. In fact, we can be pretty sure of one thing, that this register has changed since then, right? Because this register contains whatever the previous whatever. So here we're running instruction 0. Here's instruction 1. Here's instruction 2. This is instruction 3, right? So we know for sure what's in this register is wrong, okay? And that's what's telling us, if you remember, which register in the register file we have to update. Okay? So we're in kind of a time warp here. Okay? Because we had to go back around, and unfortunately our information on where to write the register isn't sitting here anymore. So we have to do one thing, right? So that's the problem. If we just read from our input register, we'd get the wrong, it would tell us to update the wrong thing. And so what we're going to do, and this is a little hard to see, and I'm sorry about that, it's from the book. We're actually going to carry along additional information in these registers. So not just what's coming out of the previous step, but anything else we're going to need. So as we're moving stuff through these registers, they're not just individual registers, they're going to keep other stuff as well. And in particular, one of the things you're going to need, especially, you'll need it for load instruction, or for actually any instruction that's going to go back and update the register file. You need to know which register you want to update. So that's got to be carried all along. And as long as it's carried through that whole pipeline, then we can wire things together. We can say, okay, the right register, remember that RW input into the register file, we're going to get that out of this last output register. We're going to come around and put it right in there. We're not going to read it directly from the instruction originally, okay? Because that would be the wrong timing. Okay, go ahead.
Do you also have to carry control signals with you then? Because isn't there a bit that says whether or not you're supposed to write this to the register?
So are you carrying the control signals with you too? Yeah. So I believe, let's see, how are the control signals working? That's a good question. You are definitely going to have to make sure that the control signals are happening at the right time. And whether you're carrying these through the registers or through some other logic is a good question, which I will make sure I know the answer to next time. But absolutely, for the same reason here, you got to make sure those control signals are set properly. So for example, here we have this write data control signal. That has to be from this instruction, not from that instruction, right? Not from that one. So you probably what you're doing is just carrying the whole instruction along, and then it has the information you need. Okay, a couple quick questions. Yeah.
If you execute instructions every tick clock, you have to back to back to back. Then what if a second instruction depends on the result in addition to before it?
Yeah, this is fine. If the result of one instruction is dependent on something that its previous instruction did, this should still work.
On the register value, you give the previous instruction.
Well, okay, good question. It can't be, if you're pipelining these things, it can't be the instruction right before it, because it takes you 5 pipeline cycles to get, it takes you, 5 ticks to get through an instruction. So you'll have to either stall that guy or rearrange things so that you do something else in between. But you can't do it in exactly the next tick because you won't even have the answer until the end of the you can't use an answer until you've done all 5 steps. So that's a really important point. I think you had your hand up first. Yeah. Go ahead.
I was just saying that for the control signal, the logic for the control seems pretty simple and wouldn't take too long in terms of dealing.
Right.
So you could do you could as a big decoder, you could also calculate all the control signals, then pipeline the control and just send the appropriate one to your dictator.
Yeah, right. So we're either pipelining the control or we're carrying the instruction along with us and doing the control right then. And I got to figure out which one we're doing for sure. One more question, and then was there another? Okay, so I think we're out of time at this point. So what we're going to do? Let me just tell you where we're going with this. Next time we're going to start talking about all these questions that you guys asked in terms of what happens, if I do a branch or a jump. What happens if there's a memory delay and so on. And then we're going to figure out how we can get this whole pipelining thing to work.